Hi, my name is Emma. I'm a chemical engineering student at the University of Cincinnati. And in this video, I'm going to be describing the temperature pressure relationship with altitude in an isentropic system or atmosphere. So an isentropic atmosphere is both adiabatic and reversible, meaning that there is no change in heat and that the external pressure is always going to be equal to the internal pressure. I also want to note that we're only dealing with 1 mole of gas, and that would be ideal gas as well in this video. So N is always going to equal 1 in all of our equations. So we're going to start out with these 4 equations that I already have listed. The first one is the law of statics, and it states that the change in pressure with respect to position is equal to density times gravity. The second equation that I have listed is the ideal gas law, which states that pressure times volume is equal to the number of moles times the ideal gas constant times temperature. And again, our N is always going to equal 1, so it'll be pretty much irrelevant in this video because it will just cancel out. And then for number 3, we have the change in energy is equal to the small change in heat minus pressure times change in volume. And once again, we're dealing with an adiabatic system, so the change in heat is actually going to be 0, ultimately making it inevitable or irrelevant as well. And finally, we need to know that the specific volume at constant pressure is equal to the specific volume at constant volume plus the specific heat at constant volume plus the ideal gas constant. Okay, so let's get started. We're going to end up with 2 equations, one being the final temperature of the system and in relationship to the initial pressure and temperature, and one being the final pressure in relationship to the initial temperature and pressure with respect to position. Okay, so we're going to start with the first equation, which is, again, the change in pressure with respect to position is equal to density times gravity. And we know that density is equal to mass over volume, and mass is equal to the number of moles times molecular weight. So we can use the ideal gas law to rearrange this completely by rearranging it to number of moles over volume, which is equal to pressure over the gas constant times temperature. So we get that density is equal to molecular weight times pressure over ideal gas constant times temperature. So we can change our first equation to look like this. And I'm going to rearrange that just to make it a little bit simpler in the end by getting pressure on one side. And I'm going to call this equation A because we're going to end up coming back to it later on. So we need it in our back pocket. Okay, so now that we have equation A, I'm going to bring out our third equation listed, which is the change in energy is equal to the small change in heat minus pressure times change in volume. And once again, this is 0 because we're dealing with an adiabatic system. So from here, we can rearrange the ideal gas law once again to sub in for pressure. So we'll have negative RT over V times dV. And we also need to know and note that the change in energy for an ideal gas is the specific heat at constant volume times the change in temperature. So we can turn that du into CV dt, since we're working with 1 mole of an ideal gas. All right, so from here, we're just gonna integrate. So I'm gonna divide both sides by t so that we have dt over t, and our specific heat is going to be a constant. And obviously the ideal gas constant is also constant. So then we have this. So on the left-hand side, we're integrating from some initial temperature T1 to a final temperature T2. And on the right-hand side, we're integrating from some initial volume V1 to a final volume V2. Now I'm going to evaluate these integrals, which will both be natural logs. So this one will be the natural log of T2 over T1. This one will be the natural log of V2 over V1. Then I'm going to divide both sides by specific heat, and due to natural logarithm laws, we can raise that right-hand side to negative R over CV. And then from here, we will be able to exponentiate both sides to get rid of those natural logarithms. So then we are left with T2 over T1 equal to V2 over V1 to the negative R over CV. And now I want those volumes to go away. I want them to be pressures and temperatures. So once again, the ideal gas law comes in handy, and we know that V2 over V1 is equal to R times T1 or T2, sorry, over P2 over R times T1 over P1. So these R's cancel, and then we can sub that back into our equation. So we have T2 over T1 equal to T2 over P2 times P1 over T1, all raised to the negative R over CV. Okay. So from here, we are able to get all of the temperatures on one side and all the pressures on the other side. And all that takes is a little bit of rearranging of the exponents so that, and divide by the temperatures. So on the left-hand side, we will have T2 over T1 to the 1 plus R over CV. And then on the right-hand side, we will also flip so that we have P2 over P1 times R over CV, since that will just go to a positive. Okay, so we're not going to use our equation 4 that we noted at the beginning, which is that the specific heat at constant pressure is equal to specific heat at constant volume plus R. And there we can sub this in for our exponents. So we'll end up with T2 over T1. And then we'll have CP over CV here. Okay. And now, to make things simpler, I'm going to make CP over CV equal to K, variable K. So then we will have T2 over T1 is equal to K. Oh, raised to the K, excuse me. And then P2 over P1 is going to be K minus 1. Now, I just want, we're solving for T2. So I'm going to raise both sides to 1 over K, and then I'm going to divide by T1 so that we can have our T2, our final temperature equation, which is going to be T2 equals T1 P2 over P1 to the K minus 1 over K. And I'm going to call this equation B, because once again, we need this in our back pocket because we're going to come back for it. All right, now moving on to a new page. We're going to bring back equation A. Which was dP over P is equal to negative mg over RT. So I believe, oh, times dc. Okay, so for here, we're going to move temperature over to the left-hand side. So we have T over P, dP to this. And then we are going to integrate, oh, but we're going to integrate this, left the T over. Okay, so we're going to integrate this in regards to pressure. So some initial pressure to some final pressure. And then we're going to integrate this side in regards to position. So we'll go ahead and leave mg over r out of it because they are constants. And we're going to integrate from some initial position to some final position. This integral is going to be super easy. It's just going to be delta z. And then for the integral on the left-hand side, we're going to need our equation b, which we just solved for. So I'm going to go ahead and write that one out so that it's easy to sub in. And that was T2 equals T1, P2 over P1. And then we're able to plug that in for T. Okay, so now we're going to pull out our constants, which are T1 and P1. So this P is basically like our P2, our final, from the original equation. Okay, so now we are going to evaluate the integral. So it's going to be 1 over k minus 1 over k times p to the k minus 1 over k from that initial pressure to the final pressure is equal to our right-hand side. And I also am going to multiply the right-hand side by those constants that were left on the left hand. So we will have over here p to the k minus 1 over k over t1. Okay, so from here, we can go ahead and extend this out and move this probably to the other side as well. I forgot about that one, but that will give us P2 to the K minus 1 over K. It's a bit repetitive. Minus P1 to K minus 1 over K. And then over here, and we forgot our temperature. We can stick it right there. Okay, so now you may notice, now you may notice that we have a P1 to the K minus 1 over K on both sides. So I'm going to move that over and sub that out, and then we're getting closer to solving for final pressure. So we can do P added over here, multiplied by 1, since we have this initial one. And then we have all of our stuff from before. So K minus 1 over K. Okay. So finally, we can raise both sides to K over K minus 1 so that we can finally have our final pressure equation. So P2 is equal to P1, 1 minus K minus 1 over K times mg. And then this is all raised to the K minus 1 over K. All right. So here we have our final pressure equation where initial pressure and initial temperature are both variables, as well as change of position, which would be your altitude, to find that final pressure. And lastly, we are going to use this equation to also get a final temperature equation. So I will just do that underneath really quickly. So if we bring back equation B, we have the T2 is equal to T1 times P2 over P1, it's K minus 1 over K. And we can use the P2 equation in here, plug in. P1. So our P1s cancel, and we are left with our final temperature equation with initial temperature and change in position as variables. So now we have both of our equations, and these equations give that temperature pressure relationship with altitude and an isentropic atmosphere. Thank you for watching.